pleasure to be here today after the first special session on crowdsourcing in New York. Now we have this and urban climate informatics as a part of the regular program, which I'm really proud of. And I'm also really happy to present this on behalf of Daniel Fenner, who is the main author of this study. And I guess everybody who's dealing with crowdsourcing will know Daniel Fenner, of course. But what you may not all know is that actually he spent 1 year at my team at Ruhr-University Bochum before he moved to Freiburg, to Andreas. And what we present here is the result from a project in Bochum, which is called NLIGHT, the pointer is working a bit, which stands for Enabling Analysis of Global Urban Heat. And the title is Global Analysis of Intra-Urban Air Temperature Variation using crowdsourced weather station data. So not really working.
Point at the screen.
There's a kind of
Yeah.
it's not changing.
There we
Okay. So why do we want to do this? I mean, there are several ongoing discussions in the field for a very long time, and one of this is we need to go beyond case studies. So I mean, that's the point Ian made, and also many others, that the urban heat island always focus on single cities, and we need to get a means to actually make comparative studies over the globe and also in different microclimate zones. Then, of course, you all know that we have really heterogeneous air temperature conditions within city, which depend on urban form, but also then have a specific diurnal course and seasonality, and so on. But there's another discussion which has been started by Alberto Matthias and also Negin and colleagues, that actually we may want to focus more on the intra-urban variation instead of just this urban heat island, which is also has the problem that it has a rural reference which is not well defined, and much of this actually depends on the reference. The problem in doing so is that urban observational networks are still sparse, even if there have been growing efforts and they are being implemented, but also it always shows that it's really difficult to not just implement them, but in particular to maintain them over a long time. If they're attached to a specific scientific project, you may be able to do this for 2 years, but then it's really always the problem what comes afterwards. So we need a consistent methodology to compare cities globally, and that is challenging. And being in this session, it's not a big surprise what we're going to suggest also regarding the title. How can we do it? We can do it using crowd weather station data. So these are privately owned weather stations, like the examples here shown from NetAtmo. And we previously also called them citizen weather stations, but now moving more to the term crowd weather stations. I tried to do this throughout the talk, but I may fail in between. So they are emerging source for various urban climate applications, and there are just a number of recent references. I think I see many people in the room who actually could be added here to this list. And what we want to ask here is, can we actually take this to the next step and use this data to make not case studies, but a global scale analysis of urban climates. So what are the data we're using? We put together a crowdsourcing database of more than 500 cities, starting in 2019 in 1 hour temporal resolution. And we have more than 300,000 stations, and resulting in more than 6 billion observations of individual air temperatures over this time. They are all quality controlled using the quality control package also developed by Daniel himself. And then we add some additional data, in particular the global human settlement urban center database, some coastline data from natural earth, some elevation data for lapse correction, and then also, very importantly, the local climate zone data from the global map produced by Matthias, also in Bochum. We call this the CrowdDB, crowdsourcing database. And if you're interested in this, there are going to be 2 more talks on this. My student Jonas, who is chairing the session, is also going to present the database tomorrow afternoon, and some other applications. And Matthias is going to present the global map in the boot-up session on Friday morning. So I highly recommend to attend these 2. So what are we doing with the data? So first, we select data points according to the local climate zones. So we assign the mode class, and then we filter for some minimal fraction of the specific climate zone according to the similarity in the surrounding. Then we do some time adjustment to adjust to local solar time. We do some height correction using just a standard atmosphere and the geometric collapse rate. And then we group the data. That means we result with one value per LCZ and city. At this point, we lose all the spatial information. So we just look at this as a problem, LCZ and city, and then we make a further filtering step. So we only take data which has 5 stations per LCZ and city, and we only take data that has a availability of more than 80% over 2 years. And then finally, we aggregate this per month and hour. And a problem resulting from doing this type of global analysis is that, of course, we have very different microclimates. So we have very different temperatures. It doesn't make sense to compare absolute temperatures at all. So therefore, we need some relative indicators, and that can either be temporally or it can be spatially. And therefore, we look at heating and cooling rates. So the first question is, how do urban form and function influence heating and cooling rates within cities? And the second one is, how are intra-urban air temperature differences per LCZ characterized on a global scale? So we look at spatial differences between LCZs, between different urban structures. So what are the data we get? I want to show this here. And I mean, you immediately see that we somewhat fall short of the claim to do a real global analysis, because also here the data availability is still heavily biased towards the global north, because for many people in developing countries, it may not be a top priority to buy a weather station for 200 euros, which is quite evident. But then on the other hand, we're positive that we do have data from at least 4 continents here. And the colors indicate microclimates. And if you look at this, you see that also they are most in sea climates, since they are heavily biased to Europe. But they're quite a lot in D and B climates as well, while the tropics are still very underrepresented in the data set. Second point is if you look at the distribution of LCZ within the cities. So that's the number of cities that have the particular class. Then most common is LCZ 6, and 2, 5, and 8 are very frequent, while the others are rather sparse too. So what do we get? We'll look at the heating and cooling rates first. And here we can clearly see that the heating and cooling is dampened for classes with higher buildings, and also for denser buildings. So that's the first one. For instance, here, if you look at LCZ1, and that's actually what you would expect, because there's more heat storage is going into the heat storage in the morning, therefore you have a reduced heating rate. And you can also see very well the seasonality of this. So the solid line is the summer, and summer of spring have higher rates in comparison to winter and autumn, which is also not very surprising, but it's really nice that it comes out like this from the data. And we can see that there's also a time lag, which is a result of the sunrise being later in winter in comparison to summer. So you can really nicely see that here. And what's also interesting that's not shown here on the slide is that this heating and cooling is dampened in coastal cities. So we can also use this to not only compare macroclimate zones, but also we can start seeing topoclimatic effects really in these data, comparing coastal cities, non-coastal cities, mountainous setups, and so on. So we're just starting. So that's the second one, looking at the intra-urban differences. So that's now the differences between LCZ classes. As we don't have as rural reference for the classical heat island, so that is the urban heat island as defined by Ian Stewart in his paper, which is differences, intra-urban differences between different LCZ types. And as you've seen the distribution of the LCZ, the most frequent one is LCZ 6, and therefore we use this as a reference for all other classes. So what you see here is always the difference between the respective LCZ and LCZ 6. And there also you can see a lot of features which you actually expect, or it's really nice how they come out. So first, look at the diurnal cycle. You have the most, the strongest intra-urban heat differences during nighttime, as the classical temporal urban heat island pattern would be. So during nighttime and the early morning hours, while during daytime there's close to no intra-urban differences, or there may even be a small cooling effect relative to LCZ6. So we have an intra-urban cool island, if you want to call it like this. So this is really nice. Secondly, you can again see the seasonality, which also comes out really, really nicely. And then you can now start looking at the differences between the LCZ classes, which was actually the main aim of this analysis. And you can see that it's much more pronounced for the higher and denser classes. So we have the strongest signal here for LCZ1, which is high and dense. And we have a strong signal for LCZ4 and 2. So 2 would be dense and 4 would be high. There's also quite a strong signal for LCZ10, but here we have to be a bit careful because you remember there was just one station in there. What we neglect here is the variability between the cities, and therefore we now look at this one, where so we have to neglect the diurnal cycle now, so we just look at an average of the night hours instead. And here the distribution, the box plots show the distributions over the stations, and each point shows a city mean. And essentially you can see the same thing again, that urban form matters. You see the effect of building height, and you see also the effect of building density. So height would be here comparing LCZ1 with 4, for instance, and density that would be density, and height would be comparing LCZ1, 2, and 3. I jump over the seasonality here because I really want to present this as a last highlight. So being 50 years after the very famous paper of Tim O on city size on the urban heat island, we thought this would be a great chance to actually revisit this on a much larger database. And even though I know that it's not Tim's favorite paper, I think it's really interesting to look at this. In this respect, so what do? We look at all these cities for Europe. So now we just look at the summer months, aggregated value for summer months. So Tim did it for maximum heat island intensities. And here we look at the mean summer heat island intensity, again, for a class difference between 2 and 6. And that means we lose some of the cities because they don't have enough stations in 2. And what you do see here is a very clear relation between the heat island intensity and both the population, as it was done in the paper, and also the built-up area. So I think also population in Tim's sense is more a proxy of urban structural characterization, which is related to the size of the city, which is more relevant. So you can clearly see that, even if there's some variation. And secondly, you can see that the coastal cities, in comparison, have a slightly damped urban heat island again. And that is just to showcase what type of analysis you can now start doing with this data being available. So that's not the end, that's just really the start. And I jump over some of the conclusions. We go to the outlook. So we still have to know that we have an unequal distribution. This is a problem, but actually we can overcome this because they are not so expensive. So it's not unrealistic to say in a big project we equip another 20 tropical cities with 50 sensors. So that's absolutely doable if we have connections in there. And secondly, in this type of study, we had to aggregate a lot to actually use this global data, but then we neglect all the micro-scale variability and also the spatial effect. And if you're interested in this, I just made some advertisement again for Jonas' talk tomorrow. Thanks very much, and I'm happy to take questions.
Thank you. Maybe there's time for a short question. Yeah, you are first.
How did you manage to download so many Netatmo data?
I passed this question to Jonas, who did most of this work, and you're going to answer it now, but tomorrow it is talking. So
Yeah,
be there.
please come to the talk.
Thank
For
you.
afternoon. So time is the key.
Yeah, so the next presenter is Sarah Top. Thank you for your presentation.
Yeah, thanks.